Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting into the vast and powerful world of monsoons. These are not just rainy seasons. They are immense breathing patterns of our planet, where winds reverse direction and oceans lend their moisture to distant lands. Entire harvests rise or fall with their arrival. Rivers swell. Deserts bloom. Cities wait for the first rumble of thunder on the horizon. A monsoon is movement on a grand scale. It is heat and water and wind, all woven together in a rhythm that has shaped civilizations for thousands of years. Trade routes once depended on it. Forests and wetlands still do. Even the air above mountain ranges can be transformed when these seasonal monsoons begin. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do. Let your shoulders soften. Let your breathing slow. Allow your thoughts to drift as we explore the vast seasonal heartbeat of our world. Let's begin. Monsoons are seasonal wind reversals that can reshape whole continents. For part of the year, air flows one way across an ocean and into land. Then, as seasons turn, the direction flips and the whole map of moisture changes with it. That shift can steer where storms gather, where rivers rise, and where soils store water for months. In South Asia, the pattern links coastlines to Himalayan valleys through a moving river of air. In West Africa, it can decide how far north grasses will grow before the dry season returns. Even far offshore, the changed winds can rearrange surface currents and the zones where fish feed. When you zoom out, it feels less like weather and more like a planetary habit. It is a repeating rearrangement of the atmosphere that nations plan around. A monsoon is driven by land heating faster than the ocean nearby. In sunlight, soil and rock warm quickly, while water heats more slowly and holds its warmth longer. That contrast sets up a tug-of-war in the air above. Warm air over land becomes lighter and rises, which leaves a kind of empty space that needs to be refilled. Air from over the sea moves in to replace it, and it brings water vapor along for the ride. As the year progresses, the balance shifts again. Land cools faster than the ocean after summer fades, and the flow can swing the other way. What sounds like a simple difference in heating becomes a seasonal engine. It is powered by the basic physics of warmth and weight in the air. It can turn a coastline into a doorway for clouds. Monsoon rains can deliver most of a region's annual water in months. Imagine a place where the landscape receives its main drink in a single long season. Reservoirs, rice paddies, wells, and even household routines are built around that timing. When the wet months arrive, rivers can swell from modest channels into wide, fast-moving corridors that spread across floodplains. Water seeps into soils and rock, storing itself out of sight for the coming dry stretch. Farmers can plant with confidence when the pattern is steady, because one successful season can support food for the whole year. City planners also depend on it. A drainage system that works in spring can fail in a single intense monsoon afternoon. In many regions, the calendar is not defined by temperature. It is defined by when the sky opens. The same monsoon can bring floods one week, then drought the next. Monsoon seasons are not always a smooth, reliable pour. They can pulse. One stretch brings relentless rain that saturates hillsides and pushes rivers past their banks. Then the storms can retreat for days or weeks, leaving fields thirsty under bright sun. This swing matters because the ground does not reset instantly. After flooding, soil can crust and harden. so the next rain runs off instead of soaking in. After a dry break, plants can become stressed, which makes the return of heavy rain more damaging. Even drinking water systems can be whiplashed. Wells may turn cloudy after sudden runoff, then drop quickly if the pause drags on. This is one reason the season feels dramatic to people who live within it. The same large-scale pattern can deliver both too much and too little, almost back to back. The monsoon's first storms can arrive like a moving wall of humidity. Before the rain truly commits, the air often changes first. A dry breeze is replaced by a heavier flow that feels warm and damp on the skin. Nights can become stickier, and the scent of water seems to hang in the background even before the first downpour. Then the sky begins to stack clouds in layers, and distant thunder becomes more frequent. In some places, the onset is announced by a line of storms that marches forward over hours, bringing gusty winds ahead of the rain. That first burst can be thrilling and unsettling at once. Dust is knocked down. Leaves shine. Streets that have baked for months suddenly reflect the sky. People notice how sound changes as well. A city can grow quieter under thick cloud cover, then erupt into the white noise of rain. The arrival is not only a forecast, it is a sensory shift that tells you the season has turned. Monsoons are not just rain, they are giant wind systems. Rain is what most people remember, yet the deeper story is moving air. Seasonal winds can stretch for thousands of miles, linking the sea surface to inland plains and mountain walls. Those winds push moisture, heat, and even particles like dust and smoke from one region to another. They can shape ocean upwelling along some coasts, which can lift cold, nutrient-rich water toward the surface and change where fish gather. They also steer storms. A shift in wind can guide a cyclone toward land, or it can shear storms apart before they strengthen. Even outside the wettest months, the winds can influence humidity and nighttime temperatures. To understand the season, you listen for more than thunder. You watch which way the air is flowing. It is a seasonal circulation, and the rainfall is one expression of it. Mountain ranges can squeeze monsoon air into sudden, intense downpours. When moist air meets a wall of terrain, it has limited options. It can stall, flow around, or rise. Rising is the pathway that turns invisible water vapor into cloud droplets. As the air climbs, it cools, and the moisture condenses into thick cloud layers that can unload rain for hours. That is why windward slopes can be drenched, while nearby lowlands stay relatively dry. It is not only about height. The angle of the mountain face, the shape of valleys, and the speed of incoming winds can focus rain into narrow corridors. Some towns learn the pattern street by street. One hillside receives repeated soaking storms, while another ridge, only a short drive away, gets lighter showers. In extreme cases, this squeezing effect can turn a humid afternoon into a violent cloudburst. Water arrives faster than rivers can carry it away. Monsoon clouds can rise higher than many commercial flight paths. In the strongest storms, warm, moist air rockets upward like an elevator with no stops. As it climbs, it builds towering clouds that can punch into the upper atmosphere. At the top, spreading anvils can fan outward for miles, casting huge shadows that change the light on the ground below. Inside, ice and water collide, which helps create powerful lightning and heavy rain that can fall in sheets. Pilots plan routes around these storm towers for good reason. The turbulence can be severe, and the structure of the cloud can shift quickly as the storm feeds on heat and moisture. These clouds are also part of how the planet moves energy. They carry warmth upward, then release it high in the sky when water vapor condenses. From the ground, they look like mountains made of vapor. From above, they can look like bright white continents floating in the air. A strong monsoon can cool daytime temperatures by blocking sunlight. When cloud decks thicken, the ground receives less direct sun, and that changes the whole feel of a day. Surfaces that would normally heat quickly stay closer to the air temperature, which can reduce the sharp afternoon peaks that build in pre-season heat. Rain also cools by evaporation. Water on skin, soil, and rooftops draws heat as it turns to vapor, which can make the air feel noticeably different after a storm passes. This cooling can be a relief, yet it can also influence everything from electricity demand to crop growth. Some plants thrive when heat stress eases, while others need bright light and can slow down under persistent grey skies. Cooler days can also slow the formation of certain pollutants that build in stagnant heat. In that sense, clouds act like a temporary dimmer switch on the landscape. The season does not only add water, it can reshape the daily rhythm of temperature. When the monsoon fails, food prices and livelihoods can shift fast. A weak season is not just disappointing weather. It can ripple outward through farms, markets, and households with surprising speed. Crops that rely on timely rain may germinate poorly, or they may never reach full yield. Pastures can stay sparse, which stresses livestock and pushes herders to travel farther for forage. Hydropower can drop when reservoirs fail to refill, and that can raise costs for businesses and families. Cities can feel it too. Water restrictions may appear, and heat can become more intense without the usual cloud cover. The impacts are uneven. A few missed weeks can be manageable for well-irrigated farms, while rain-fed regions can face serious strain. In many places, the season is tied to seasonal work, debt cycles, and migration decisions. When rain arrives late or not at all, people adapt quickly. They change what they plant, what they buy, and sometimes where they live. India's summer monsoon is powered by heat over the subcontinent. As late spring turns into early summer, the land warms so strongly that air over northern India and Pakistan rises in vast columns. That rising air helps form a broad, low-pressure region that acts like a seasonal magnet. Moist winds respond, sweeping in from the surrounding seas and curving across the country. The rains do not arrive everywhere at once. They advance in stages, with coastal storms often leading the way and inland regions following as the circulation strengthens. High above, the atmosphere reorganizes too. Bands of clouds and storms align into a new summer pattern, and the jet stream shifts position. This is why the season can feel like a switch flipping. Heat builds, the air becomes heavy, and then the sky finally breaks into the months that refill rivers, reservoirs, and fields. The winter monsoon can reverse winds and dry out huge areas. When the land cools after summer, pressure patterns change direction and the airflow flips. Over much of South Asia, winds blow outward from the continent toward the ocean, carrying drier air that can clear skies and sharpen the feeling of cool nights. In many regions, this is the season of dust, long sightlines, and crisp mornings. Yet the reversal is not simply a dry ending. In southeastern India and Sri Lanka, the same seasonal flow can pick up moisture over the Bay of Bengal and deliver important rains to places that are comparatively dry in summer. That is why farmers in Tamil Nadu often watch a different calendar than farmers in northern India. One name can describe a whole family of seasonal shifts, with winners and losers depending on where the winds travel and what water they gather. The Bay of Bengal often feeds some of the heaviest monsoon rains. This warm bay is like a moisture reservoir pressed against a crowded coastline. During the season, clusters of low-pressure systems can form over the water and then drift inland, bringing days of steady rain rather than a single dramatic storm. These systems can travel far, watering plains and river basins deep inside the subcontinent. The bay's shape also helps concentrate the flow of humid air toward the northeast. That is one reason parts of Bangladesh and India's northeast can see long spells of intense rainfall that seem to arrive in waves. When those rains meet already swollen rivers, the effect can feel unstoppable. For people living near the coast, the bay can be both a giver and a threat. It can sustain rice fields and freshwater ponds, and it can also drive dangerous flooding when storms line up one after another. The Arabian Sea helps fuel powerful rain bands along India's west coast. On the west side of India, the season often arrives with a dramatic surge of ocean air. Winds can strengthen into a fast-moving corridor that carries moisture toward the coastline, and long bands of rain can organize offshore before sweeping onto land. Fishing communities notice the change quickly. Seas can grow rough, and the pattern of currents and surface water shifts in ways that affect where boats can safely travel. Coastal cities feel it too, because the first heavy rains can arrive after weeks of heat, when streets and drains are not ready for sudden volume. Farther south, the same ocean source helps keep the air humid enough for long, soaking rains that support plantations and forests. It is easy to picture the season as clouds forming over land, yet a great deal of the story begins at sea, where warm water loads the air with invisible fuel. The Western Ghats can trigger rain on one side and dryness on the other. This mountain chain runs like a spine near India's west coast, and it helps create striking contrasts over short distances. On the coastal side, the wet season can feel relentless, with repeated showers that keep streams flowing and hillsides green. Cross the range toward the interior plateau, and the landscape can change into a far drier rhythm, where rain is more limited and reservoirs matter more. These contrasts shape everyday life. Building styles, crop choices, and even the timing of local work can diverge from one valley to the next. The biodiversity story changes too. Lush forests and amphibian-rich wetlands thrive where water is plentiful, while tougher dry season species dominate where moisture is scarce. For travelers, it can feel like passing between climates in a single day. For residents, it is a reminder that geography can draw sharp lines through the same season. Bangladesh's lowlands can amplify monsoon flooding with river surges. Bangladesh sits at the meeting place of some of the world's great rivers, and much of the country lies only a little above sea level. During monsoon season, rain falling hundreds of miles away can arrive days later as a rising wall of water moving downstream. When several river systems peak together, the floodplain can spread into a temporary inland sea. Add high tides along the coast, and water can have fewer places to go. Yet these floods are not only disaster, they also carry fresh sediment that helps build and renew the delta, which is one reason the land can be so fertile. People adapt with raised homes, boats as everyday transport, and crops chosen for wet conditions. Still, the balance is delicate. A season that is slightly stronger than usual can overwhelm embankments and force rapid evacuations across wide areas. The Himalayas help trap moist air and steer monsoon circulation. This immense wall of mountains shapes the monsoon in ways that are felt far beyond the peaks. It blocks cold air from the north from spilling too easily into the subcontinent during summer, which helps maintain the heat patterns that support the season. It also redirects the flow of moisture, guiding winds along the foothills and influencing where storm tracks prefer to travel. High-altitude valleys can receive summer rains that would otherwise drift away, while other regions remain comparatively sheltered. Even the snow and ice up high play a role, because they affect how the land surface absorbs sunlight and warms the air above it. The Himalayas do not just sit under the weather. They help choreograph it, shaping the boundaries where humid air gathers, where storms persist, and where seasonal winds turn. In a real sense, the monsoon carries the fingerprint of the world's highest mountains. Monsoon break periods can pause rainfall even in peak season. In the middle of what should be the wettest weeks, the sky can suddenly hold back. Clouds thin, sunlight returns, and the air can turn hotter than people expect for that time of year. These pauses happen because the monsoon is not a single storm. It is a shifting pattern that can reorganize within the season, sometimes moving the main rain belt away from a region for days at a time. For farmers, a break can be nerve-wracking. Seeds may have sprouted, and young plants can suffer quickly if the soil dries under strong sun. For cities, the pause can be misleading, since it may be followed by an abrupt return of heavy rain that hits hardened ground and rushes into drains. Breaks can also affect health by increasing heat stress when humidity stays high, but shade from clouds disappears. The season keeps moving, but it does not always pour. The onset date can vary widely from year to year. Some years, the first widespread rains arrive early and feel like relief. Other years, weeks of waiting stretch into anxiety as heat builds and water demand rises. This timing matters because it sets the pace for everything that follows, from planting decisions to reservoir planning. The reasons for the shift can be complex. Ocean temperatures, changing wind patterns, and the position of large-scale weather belts can all nudge the season forward or hold it back. Even distant events in the Pacific or Indian Ocean can alter how moisture is transported toward South Asia. A late start does not always mean a weak season, yet it can compress rainfall into a shorter window, which raises the risk of intense downpours and runoff. People often talk about the monsoon like a familiar visitor. That visitor does not always arrive on the same day, and the difference can echo across an entire year. Farmers often time planting to the first dependable monsoon bursts. The many rain-fed farms, the opening rains are not just weather. They are a starting signal. Plant too early and seeds can fail if the soil stays dry afterward. Plant too late and crops may not mature before the season fades. Farmers watch for signs that the rains are settling in, such as repeated storms over several days and moisture that sinks into the ground rather than vanishing by afternoon. In some regions, traditional knowledge and modern forecasts work side by side, with radio updates and phone alerts supplementing local observation. The choice of crop can hinge on early season rainfall too. A promising start may encourage rice or other water-loving plants, while uncertain conditions can push farmers toward hardier options. This timing influences labor, loans, and market supply months later. When the first reliable rains arrive, they do more than wet the soil. They set whole communities into motion. The East Asian monsoon shapes rainfall from China to Japan. Across East Asia, the wet season is not a single local event. It is a sweeping seasonal shift that links coastlines, river basins, and islands under one changing pattern of winds and pressure. When the circulation sets up, rain belts can stretch for great distances, lingering over one region while another waits. The result can be weeks of steady soaking in the Yangtze Basin, followed by a later turn toward Korea and Japan. These rains help fill reservoirs and sustain crops, yet they also test cities built beside rivers that can rise fast. What makes it so captivating is the scale. A pattern that begins with warming land and nearby seas can shape daily life across multiple countries. It is like watching weather become geography as the season draws a moving boundary between dry and wet. Summer monsoon winds can carry ocean moisture deep inland. Air over the ocean can hold an enormous amount of invisible water, and summer winds act like a delivery system that moves that moisture far from the coast. Once that humid air travels inland, it meets heated ground, rising terrain, and turbulent afternoon warmth that encourage clouds to grow. Rain can fall hundreds of miles from the shoreline that supplied the vapor. This is why some interior regions can receive life-changing rainfall, even though they sit far from open water. It is also why an ocean heatwave can matter to farmers inland. Warmer seas can load the air with more moisture, and that can raise the odds of heavier downpours when storms finally form. The journey is continuous. Ocean evaporation, wind transport, cloud building, and rainfall are all chapters of one moving story, and the land far inland reads the ending. Winter monsoon winds can bring cold, dry air over warm seas. In winter, strong winds can surge outward from cold continental interiors and sweep across warmer ocean surfaces. That meeting can be dramatic. The air begins dry and chilly, yet as it races over warm water, it can pick up heat and moisture from below. The result is often unstable weather offshore, with lines of clouds and bursts of snow or rain forming downwind. Coastal regions can feel sudden changes in wind and wave conditions, even when skies inland remain clear. It is a reminder that the season is not only about summer rain. Winter brings its own style of power, with sharp pressure contrasts and persistent flows that can last for days. This pattern also influences air quality, since dry winds can transport dust and pollutants long distances. Over warm seas, even cold air can become stormy once it has traveled far enough. The Mayu and Bayou rains are linked to East Asia's monsoon front. Early summer in East Asia can be marked by a long-lived band of clouds that seems to hover between air masses. On one side is warm, humid air pushing north. On the other is cooler air holding its ground. Where they meet, the atmosphere can form a persistent rain zone that drifts slowly, delivering days of steady precipitation, punctuated by heavier bursts. This is not the quick drama of a single thunderstorm. It is a slow, organized system that can soak soils to their limits and keep rivers rising even without spectacular downpours. For agriculture, the timing can be both blessing and hazard. Rice fields welcome reliable water, while fruit growers may worry about rot and disease during extended wetness. The city life, it can feel like the sky has settled into one mood. Umbrellas become routine, and the sound of rain becomes part of the season's background. Korea's Jangma season is part of the same shifting monsoon belt. In Korea, early summer rains often arrive as a recognizable season with its own rhythm. A rain front can linger nearby, feeding repeated episodes of wet weather that alternate between light drizzle and heavier surges. People feel it in everyday choices. Outdoor plans become flexible, laundry takes longer to dry, and mountain trails can turn slick within hours. The season is not only about inconvenience. It is part of the water budget that supports reservoirs and crops through hotter months. It also sets the stage for later weather, since saturated ground reacts differently when intense storms arrive afterward. What makes it fascinating is how connected it is. The same broad monsoon arrangement that influences China and Japan can place this rain belt over the peninsula for a time, then lift it away. A shift in the wider circulation can change a week of forecasts. In that sense, Jangma is local, and it is also global. Japan's early summer rains are tied to a stalled seasonal boundary. Japan can experience an early summer period when a boundary between air masses slows down and refuses to move. Warm, moisture-rich air presses in from the south, while cooler air influences the north. The result is a zone where clouds build again and again, producing repeated rainfall that can last for days. Because Japan is mountainous, the impacts can vary sharply between regions. One area can see long, soaking rain, while another sees bursts that trigger quick rises in small rivers. This season is woven into daily life. Schools adjust outdoor activities, farmers plan around saturated fields, and commuters learn which streets flood first. The boundary eventually shifts, but while it lingers, it can feel like the atmosphere has paused in place. The fascination is in the balance. A small change in wind direction or temperature can nudge the whole zone forward. Until then, the country lives under a sky that keeps returning to the same story. Typhoons can interact with monsoon flows and supercharge rainfall. A typhoon is already a powerful system, yet its rain can become even more intense when it taps into a broader river of moisture, feeding the seasonal circulation. In that situation, the storm is not just carrying its own water. It is drawing in extra humid air and lifting it into rain-producing clouds, sometimes far from the storm's center. That is one reason typhoon-related flooding can strike places that are not near the strongest winds. Mountain terrain can make this worse, since moist air forced upslope can produce prolonged, heavy rainfall that keeps going even as the storm's track shifts. The most dangerous part is often the combination of timing and saturation. If the ground is already wet from earlier seasonal rains, rivers have less capacity to absorb another deluge. Emergency planners watch these interactions closely, because the hazard is not only the wind. It is the way large-scale moisture transport can turn one storm into a wide-area rain event. Monsoon timing influences rice farming across much of East Asia. Rice is a crop that thrives when water is reliable, and that makes seasonal rain timing deeply important. If steady rainfall arrives as seedlings are ready, paddies can be flooded and managed with confidence. If rains arrive too early, fields can become waterlogged before planting is complete. If they arrive late, farmers may rely on pumped water, which can be costly and limited. The timing also matters for disease and pests, since prolonged wetness can change what spreads in the field. Even the harvest window is shaped by the season. A wet spell at the wrong time can damage grain quality and complicate storage. What is striking is how many decisions cascade from the calendar of rain. Planting dates, labor schedules, water releases from reservoirs, and market supply can all hinge on when the seasonal rains settle in. In that way, the monsoon is not only weather. It is part of the agricultural clock that many communities live by. Dust and pollution can change how monsoon clouds form and rain. Air is never perfectly clean, and tiny particles floating in it can influence clouds in surprising ways. Some particles provide surfaces that water vapor can cling to, which can affect how many droplets form and how big they become. In certain situations, clouds may end up with many small droplets that stay suspended longer, delaying rainfall until the cloud grows stronger or collides with other systems. In other cases, particles can absorb sunlight and warm layers of air, which can change stability and airflow near the surface. This means a smoky or dusty atmosphere can subtly shift when and where rain falls, even if the seasonal winds are otherwise normal. The story is also personal. Cities with heavy pollution can experience different cloud behavior than nearby rural areas, and that can complicate forecasts. It is a vivid reminder that the monsoon is not just shaped by oceans and mountains. Human activity can enter the loop through the air itself. In some years, monsoon rains arrive earlier, but end sooner. A season can start with confidence, then fade before the landscape is truly refilled. Early arrival can bring relief from heat and can help farmers begin planting, yet a shortened finish can leave reservoirs below target and soils less prepared for the dry months ahead. This pattern can be especially tricky because it hides its risk. The first weeks may look generous, and that can encourage decisions that assume the rains will continue. When they do not, the consequences can appear later, during late summer heat or early autumn dryness. Scientists look for reasons in ocean temperatures, large-scale wind patterns, and shifting storm tracks. What matters to people on the ground is the mismatch between expectation and outcome. A front-loaded season can also concentrate rain into fewer weeks, which raises the chance of runoff and flash flooding while still failing to build long-term water storage. The calendar can feel familiar, yet the pacing can change the entire year's water story. The West African monsoon brings life to the Sahel's short growing season. In the Sahel, the year can feel like a long wait for a brief window of possibility. For months, dry winds dominate and vegetation holds back. Then the seasonal flow shifts and moist air begins pushing inland from the Atlantic. The first dependable rains can transform dusty ground in days, coaxing seeds to wake and grasses to surge. Fields that looked dormant become patterned with green, and herders may follow new growth across wide distances. Because the wet season is short, timing matters intensely. A good start can mean full granaries and healthier herds. A poor start can force difficult choices that ripple through families and markets. What makes this region so compelling is how quickly the landscape responds when water finally arrives. The monsoon is not a background detail here. It is the switch that turns scarcity into growth. A northward shift of monsoon rains can transform pasture and harvests. The rain belt in West Africa does not sit still. As the season develops, it can creep north, sometimes reaching farther than expected, sometimes stalling well to the south. That movement can redraw the map of opportunity. When rains push north, grazing lands that were brown and brittle can become usable again, and herders may find water where there was only dust weeks earlier. When the rain belt stays south, crops that depend on reliable moisture can struggle, and wells may drop sooner than communities expect. This shift also changes competition for resources. More rain in one zone can ease pressure there, while less rain elsewhere can intensify it. What is striking is how a change in position, not just a change in amount, can matter so much. The season becomes a moving target. People track it with clouds, wind, and radio forecasts, because a small geographic drift can decide a whole year's outcome. The Sahara's heat helps draw moist air inland from the Atlantic. The Sahara is often pictured as empty, yet it plays an active role in the seasonal drama. In summer, the desert heats intensely, and that warming can help create a broad, low-pressure region over the land. Air responds to that pull. Moisture-laden winds from the ocean begin to flow inland, and the boundary between dry desert air and humid monsoon air shifts and writhes. This contrast can energize storms, because the atmosphere is trying to balance two very different air masses. The desert also shapes how dust moves. High winds can lift fine particles into the air, and those particles can travel far, sometimes even crossing oceans. The monsoon is not only an ocean story, it is also a desert story. A place defined by dryness can help power a season defined by rain, simply through the physics of heat. The Gulf of Guinea is a key moisture source for West Africa. Along the curve of West Africa's coast, warm waters in the Gulf of Guinea feed the atmosphere with water vapor. When winds blow onshore, that moisture becomes the raw material for clouds and storms moving inland. The Gulf's influence can be felt in coastal humidity, in the early season buildup of clouds, and in the way rainfall patterns change with ocean conditions. If the nearshore waters are cooler than usual, evaporation can drop, and the air arriving on land may carry less moisture. If the waters are warmer, the air can arrive primed for heavier rain once it is lifted by heating land or rising terrain. This connection makes the coastline feel like a gateway. The ocean is not just beside the land. It is actively supplying it. When the monsoon season begins, the Gulf is part of the engine room, loading the winds with the water that will later become rivers and crops. Monsoon rainfall can arrive in pulses, not a steady daily pattern. It is tempting to imagine a wet season as constant drizzle, yet many monsoon regions experience rainfall in bursts. A few days can bring repeated storms that pound roofs and fill streambeds. Then the sky can ease off, leaving a bright stretch that feels almost like a different season. These pulses can be shaped by waves of atmospheric activity that travel through the tropics, strengthening storm formation for a time, then weakening it. On the ground, the pulse pattern changes everything. Intense bursts can cause runoff and erosion, especially where soils are bare. Longer pauses can stress crops that have shallow roots and high water demand. Water managers notice it too. A reservoir may fill quickly during a burst, then stagnate during a lull. The pulse rhythm also affects human mood. People brace during stormy stretches, then catch up on travel, repairs, and work when the break arrives. The season becomes a series of chapters. Atlantic sea temperatures can influence West African monsoon strength. The ocean surface is not just a backdrop. It is a thermostat that can nudge the entire seasonal circulation. When parts of the Atlantic are warmer, more water can evaporate into the lower atmosphere, and wines arriving on land may carry extra moisture. Warm seas can also influence pressure patterns, which affects how strongly air flows inland. When seas are cooler, evaporation is weaker, and the onshore flow may be less favorable for heavy rainfall. These differences can help explain why one year feels lush and another feels uncertain, even when the calendar looks the same. This influence matters far beyond the coast. A subtle shift in ocean temperature can alter rain chances deep inland, where people may never see the sea, but still depend on what it is doing. It is one of the most fascinating links in climate science. The skin of the ocean can help shape the fate of farms, rivers, and grazing lands far away. The monsoon can steer where locust habitats bloom or fail. Locusts are not born as disasters. Their numbers and behavior respond to the landscape, especially the availability of fresh vegetation and moist soil where eggs can thrive. When seasonal rains arrive in the right places, plant growth can surge, creating green corridors across regions that were recently dry. That new growth can support insects, birds, and grazing animals, and it can also set the stage for locust populations to expand. If rains are patchy, locust breeding areas can concentrate into fewer zones, which can increase the chances of dense swarms forming later. Farmers and monitoring teams pay close attention to rainfall maps because they help predict where risk is rising before the insects are visible in large numbers. This is a powerful example of how the monsoon influences more than water supply. It can shape ecological chain reactions. A pattern of seasonal rain can decide whether an insect remains scattered and harmless or becomes a roaming force that threatens harvests. River basins can store monsoon water long after storms end. When heavy rains fall, not all the water rushes away at once. Some soaks into floodplain soils, some seeps into shallow groundwater, and some is held in wetlands and natural depressions that release it slowly. Large river basins act like living storage systems, smoothing the extremes between wet and dry. After the storms have moved on, rivers can continue flowing strongly for weeks, fed by water that is traveling through soil and rock at a much slower pace. This delayed release can support irrigation, drinking supplies, and ecosystems that depend on steady water rather than sudden floods. It also explains why damage can persist. A basin that is saturated can remain vulnerable, so even moderate later rain can cause renewed flooding. The storage story is why monsoon management is not only about surviving storms. It is about understanding how water lingers in a landscape. The season ends in the sky, yet it continues in the ground. Coastal cities can flood when monsoon rain meets high tide. In coastal zones, flooding is not always about how much rain falls. It is also about where the water can go. During high tide, seawater pushes into river mouths and drainage channels, and that can slow the outflow of stormwater from the land. If heavy rain arrives at the same time, streets can flood quickly, even if the rainfall total is not record-breaking. The effect can be especially severe in low-lying neighborhoods where the ground sits close to sea level and the drainage system depends on gravity. This kind of flooding can feel sudden and confusing. The rain may stop, yet water can remain trapped until the tide turns. Cities respond with pumps, gates, and redesigned canals, yet rapid growth can outpace infrastructure. This is a vivid example of compound risk. The ocean and the atmosphere can team up, and the city becomes the meeting point. A monsoon storm is no longer only a weather event. It becomes a timing event. The Sahel's greening can rise and fall with monsoon variability. From space, parts of the Sahel can appear to brighten and dim across years as vegetation responds to changing rainfall. When seasonal rains are more favorable, grasses and shrubs can spread, and the landscape can look greener across wide areas. When rains are weaker or poorly placed, growth can retreat, leaving more bare ground and stressing grazing systems. This greening is not only a pretty picture, it affects soil stability, livestock health, and how much dust is kicked up by winds. It can also influence local temperatures, because plant cover changes how the ground absorbs sunlight and holds moisture. What makes the Sahel so scientifically fascinating is that it sits near a boundary between climate zones, which makes it sensitive to shifts in seasonal circulation. A small change in the monsoon can produce a large change in visible life. The land becomes a record of the season, written in color, leaf by leaf. Northern Australia has a monsoon that flips winds between seasons. For much of the year, the north of Australia breathes outward under drier trade winds. Then the pressure patterns rearrange, and the airflow swings around so moisture arrives from the surrounding seas. That switch changes more than rainfall. It changes the feel of the sky, the smell of the air, and the behavior of wildlife that has learned the timing. People in Darwin and the top end often talk about the build-up, when heat and humidity climb while storms tease the horizon. Then the real season arrives, and the daily rhythm shifts toward cloud, bursts of rain, and warm nights. This wind reversal also links Australia to a bigger tropical story. The same broad circulation helps connect Indonesia, the Timor Sea, and the Arafura Sea into one seasonal system. It is a reminder that wind can be a calendar. Australia's wet season can build storms that last for hours. Some monsoon storms are not quick flashes. They can park over a region and keep feeding on warm, moisture-rich air, which allows rain to continue long after you expect it to stop. You can hear the change in sound as the storm settles in. It starts with sharp bursts on roofs and leaves, then becomes a steady roar that blurs the edges of the world. These long storms matter because they soak the ground deeply. Creeks rise slowly, then keep rising, and roads that seemed fine at first can become impassable later. The atmosphere stays busy even when the lightning fades, because the storm system can keep lifting humid air and wringing it out as rainfall. For ecosystems, hours of rain can trigger rapid responses. Frogs call, insects emerge, and dry soils finally relax their grip. For people, it can feel like living inside weather. Monsoon bursts can refill dry riverbeds in a single night. In northern Australia, Many waterways spend the dry months as quiet channels of sand and stones. Then a monsoon burst arrives upstream, and a river can return with startling speed. You might go to sleep beside a dusty crossing, then wake to the sound of flowing water and the sight of foam and debris moving past. This is not magic. It is the result of rain falling over a wide catchment where hard, dry ground sheds water quickly into gullies, then into larger channels. The first flows often look muddy because they carry soil, leaves, and nutrients that have built up through the dry season. That moving pulse can spread life downstream. Fish and turtles take advantage of connected water, and water birds arrive to feed in newly flooded shallows. The river is not only water, it is an overnight delivery of change. The top end's wetlands depend on the monsoon for renewal. Wetlands in the top end are like living lungs that expand and contract with the seasons. During the wet months, floodplains spread out and connect billabongs, creeks, and channels into a broad, watery mosaic. This connection allows fish to move into new feeding grounds, and it provides breeding habitat for countless insects, frogs, and birds. As the season progresses, the wetlands become a giant pantry. Nutrients stirred up by flooding support bursts of plant growth, and that growth supports everything that eats it. When the dry season returns, water retreats and concentrates life into smaller pools, which makes feeding easier for birds and crocodiles. This cycle of filling and shrinking is the renewal. Without the wet season, many wetlands would stagnate or disappear, and the rich web of life that depends on them would thin out. The monsoon is not just a supplier of water. It is the reset button for an entire landscape. Cyclones can form within monsoon troughs near Australia's north. A monsoon trough is a stretched-out zone of low pressure where winds converge and storms likely gather. Near northern Australia, this trough can become a nursery for tropical cyclones, especially when ocean waters are warm and upper-level winds allow a storm to organize. At first, it may look like a messy cluster of thunderstorms. Then rotation tightens, pressure falls, and the system begins to draw in air from all sides. Once that happens, the storm can intensify quickly, because it is feeding on heat from the sea and releasing that energy as towering clouds. The danger is not only the wind. It is also the long, heavy rain that can arrive far from the exact track and the storm surge that pushes seawater into low-lying coasts. Communities watch these systems closely because they can evolve from a broad tropical mess into a named storm in a short time. Monsoon cloud cover can lower extreme heat during peak wet season. In the build-up to the wet season, heat can feel relentless, especially when skies stay clear and the sun pours down day after day. Once widespread cloud arrives, the daily temperature pattern often changes. Thick clouds reflect a portion of sunlight back to space, and frequent showers cool surfaces that would otherwise bake. The result can be fewer blistering afternoons, even though the air may still feel heavy. This matters for people working outdoors, for power grids strained by air conditioning demand, and for wildlife that times activity around heat. It can also influence how quickly vegetation dries between storms, which affects how easily grass fires can start. Cloud cover reshapes the whole atmosphere too. Nights may stay warm, while days lose their sharp peaks and the temperature range narrows. The season becomes less about searing sunlight and more about humid shade, with bursts of rain acting like a moving relief. Some Australian fires are worsened when the monsoon arrives late. When the wet season is delayed, the dry months effectively stretch longer than expected. Grasses cure, leaf litter accumulates, and landscapes that usually receive early storms remain thirsty. That extended dryness means that a single ignition can spread faster because fuels are primed and winds can be brisk. Late-season lightning can also complicate things. Storms that bring little rain can still throw sparks into dry country, creating fires that are hard to reach. Smoke can linger for days, affecting towns and wildlife, and the loss of early rains can stress waterholes that animals depend on. A late arrival also changes the psychology of the season. People who count on the first storms to ease fire risk may find themselves watching forecasts with rising tension. When rain finally comes, it can arrive in intense bursts that cause flooding on ground that has been hardened by months of heat. A delayed start can make both fire and water hazards sharper. The monsoon influences where mosquitoes breed across the tropics. Mosquitoes are closely tied to water, yet not all water creates the same risk. The wet season spreads puddles, fills containers, and floods low areas, which can create countless small breeding sites. In some regions, the first rains are especially important because they create fresh, temporary pools that warm quickly and speed up insect development. As the season continues, flowing water can wash away larvae in some places, while sheltered pools in wetlands and urban areas remain productive. This is why public health responses often track rainfall patterns closely. Timing matters as much as quantity. Communities may increase drainage efforts, distribute bed nets, or adjust spraying schedules based on expected wet periods. There is also an ecological side. Mosquitoes feed bats, fish, dragonflies, and birds, and those predators often respond to the seasonal pulse as well. The monsoon does not just change how many mosquitoes appear. It changes where they appear and how long the conditions last. Freshwater pulses can change coastal salinity and marine life. When heavy rains pour into rivers, a plume of fresh water can spread out into coastal seas like a moving lens. That fresh layer is lighter than salt water, so it can sit on top and alter the conditions that marine life experiences near the surface. In estuaries, the shift can push salt water back, which changes where mangroves, oysters, and juvenile fish can thrive. Some species take advantage of the pulse. Nutrients carried from land can feed plankton blooms, which can support food chains that rise through prawns and fish. Other organisms are stressed by sudden changes, especially if salinity drops quickly. The pulse can also carry sediment that clouds the water and reduces light for seagrass beds. Along northern Australia, these plumes can influence where barramundi and other fish concentrate, and they can reshape fishing conditions week by week. The monsoon reaches the ocean through rivers, and the sea answers back by reorganizing life near the shore. Monsoon winds can set the rhythm for seasonal ocean currents. When winds change direction for months at a time, the ocean surface responds. Currents can strengthen, weaken, or reverse, and the pathways that move heat and nutrients around the region can shift with the season. Near Australia and Indonesia, these wind-driven changes influence how water flows through straits and shelves, which affect sea temperature and where nutrients rise toward the surface. That matters for fisheries because nutrient-rich water supports plankton, and plankton supports everything above it. It also matters for coral and coastal ecosystems that are sensitive to temperature and water clarity. Even shipping can feel the difference, since seasonal winds and currents influence wave patterns and travel conditions. What makes it so fascinating is that the monsoon is not only an atmosphere event. It reaches down into the ocean and changes its moving skin. Winds write a seasonal schedule for currents, and currents carry that schedule across huge distances. North America has a monsoon that affects the Southwest and Mexico. It surprises many people that deserts can have a true wet season with a recognizable rhythm. In early summer, the atmospheric pattern over northwestern Mexico and the American Southwest shifts, and moisture begins streaming northward. The change is not a single storm. It is a seasonal reorganization that can turn dry skies into a daily question mark. In places like Sonora and Arizona, the landscape is built for waiting, then responding fast. Creosote releases its sharp scent after the first real rain. Dry washes that have been silent for months suddenly begin to speak with water. This season is also deeply regional. Coastal moisture, mountain slopes, and local heat all shape where storms ignite, which means one town may be soaked while another stays dusty. A monsoon can feel like a hidden chapter of North American climate that only reveals itself each year. The North American monsoon can trigger daily afternoon thunderstorms. During peak season, mornings can start bright and deceptively calm. Then the day builds toward convection like a slow drum roll. Sunlight heats the ground, warm air rises, and moisture waiting in the lower atmosphere finds its chance. By afternoon, towering clouds can form with startling speed, often over higher terrain where rising air is helped along. The storms can be brief yet intense, with hard rain, gusty upflow winds, and lightning that cracks close enough to feel immediate. Then, just as quickly, the cell can collapse and drift away, leaving a cooler hush and the smell of wet dust. This daily pulse shapes habits. Hikers start earlier. Construction crews plan around the afternoon window. Even wildlife adjusts, with birds and insects timing activity around the storm cycle. The pattern feels like a repeated performance, yet no 2 days deliver the same ending. Desert landscapes can flash flood when monsoon rain hits hard ground. In arid places, the ground can become sealed by heat, dust, and thin crusts of soil. When a heavy downpour strikes, water may not soak in fast enough, so it races downhill as sheets, then gathers into channels that would dry an hour earlier. The danger is how quickly it escalates. A shallow flow can become a roaring wall that sweeps rocks, branches, and debris into a narrow wash. People can be caught off guard because the rain may be falling miles away, upstream in mountains where storms are stronger. A sunny canyon can flood without warning, and the first sound may be a distant rumble that grows rapidly louder. This is why desert flood safety is so strict. The landscape does not need long rain. It needs a short burst in the wrong place. The result can remake trails, roads, and riverbanks in minutes. The Gulf of California can funnel moisture into monsoon storms. This long, narrow body of water sits beside hot desert terrain, and it can act like a corridor that helps humid air travel north. When winds align, moisture can be carried along the Gulf and into northwestern Mexico, then onward toward Arizona and New Mexico. Warm sea surfaces add extra vapor through evaporation, and that moisture becomes the invisible fuel for afternoon storm growth once it reaches heated land. The Gulf also shapes storm timing. A pulse of humid air arriving overnight can set the stage for earlier cloud building the next day. In some patterns, storms can form along the coast and then send outflow boundaries inland, triggering new storms farther north and east. It is a chain reaction powered by geography. The shape of the Gulf matters, the surrounding mountains matter, and the season's winds decide how efficiently the corridor opens. Ocean water, desert heat, and mountain lift combine into a storm recipe that is uniquely regional. Monsoon lightning can ignite wildfires even during a wet season. It feels like a contradiction, yet it happens often. Early in the season, storms can produce abundant lightning while rainfall is patchy, or it evaporates before reaching the ground in very dry air. A single strike can ignite grass, brush, or a dead snag, and wind gusts from collapsing storms can spread flames quickly. Even later, when rain is heavier, lightning can still start fires on ridges or in remote areas where a brief shower does not soak fuels deeply. Fire managers sometimes face a strange double task. They may be responding to floods in one county while tracking smoke in another. This is also why the sound of thunder can bring mixed feelings. It promises water, yet it also brings sparks. The monsoon does not erase fire season. It rearranges it, adding a new kind of ignition risk that can appear suddenly and far from roads. A single monsoon storm can refill reservoirs or overwhelm drains. One intense storm can be a gift and a problem at the same time. If the rain falls over the right part of a watershed, it can send a strong pulse into streams that feed reservoirs, boosting water supply after months of steady drawdown. The same volume, if it falls over pavement and hard-packed ground in a city, can rush into storm drains faster than they can carry it away. Streets become temporary rivers, underpasses fill, and debris clogs inlets that were designed for slower flows. The outcome depends on where the storm parks, how long it persists, and what the ground was like before it arrived. A dry basin may absorb more at first. A saturated basin may respond with immediate runoff. That uncertainty gives monsoon storms a dramatic reputation. They can be celebrated at a dam and dreaded at an intersection, all within the same hour and the same rainfall event. The monsoon can bring cooler nights by increasing humidity and clouds. After a storm day, the evening air can feel different, and not only because the ground is wet. Moisture in the air changes how heat moves near the surface, while cloud layers can reduce the sharp swings that deserts are known for. Instead of a rapid drop after sunset, temperatures may settle into a softer range, and the night can feel less stark. People notice it in sleeping patterns, in the way patios stay usable later, and in how animals remain active beyond dusk. The effect is not identical every night. It depends on whether clouds linger, whether the air stays moist, and whether winds mix the lower atmosphere. Some nights feel muggy. Others feel pleasantly tempered, especially after a strong evening downpour. This is one reason the season changes the mood of desert living. It is not only afternoon thunder. It is the way nighttime comfort can shift when the atmosphere holds more water and the sky stays covered. Habobi dust storms can form along monsoon outflow boundaries. A thunderstorm does not only rain downward, it can also push air outward like a spreading fan when cooled air sinks and rushes across the ground. In desert regions, that outflow can slam into dry soil and lift dust into a towering wall that races ahead of the storm. Visibility can drop in seconds. The air can turn gritty, and the leading edge can feel like a sudden gust front that announces itself before any raindrops arrive. These dust storms can travel miles, sometimes outpacing the rain that created them. They affect transportation, health, and even aviation, since pilots must contend with rapidly changing conditions near the surface. The most fascinating part is the structure. The dust wall often has a sharp, rolling edge, shaped by turbulent air. It is whether you can see moving toward you, like a living boundary between clear sky and a storm's expanding footprint. Mountain valleys can focus monsoon storms into narrow corridors. Mountains do more than make storms. They can guide where storms prefer to travel. Valleys can channel winds and moisture, steering humid air into specific pathways where rising motion is repeatedly triggered. Over time, certain corridors become known for lightning, cloud buildup, and sudden downpours that seem to favor one drainage over the next. This focusing effect can make forecasts tricky. A regional prediction may be accurate, yet the real drama plays out in a few narrow canyons and basins where terrain encourages storm regeneration. The consequences are practical. Roads in these corridors can be damaged repeatedly. Small communities may see frequent flash flooding, while nearby areas remain mostly dry. Even ecosystems reflect it. Vegetation can be denser along favored storm tracks, and springs can persist longer where infiltration is repeatedly fed. Terrain becomes a storm lens, concentrating energy and water into places that feel chosen by the season. Urban heat can intensify monsoon downpours over some cities. Cities are not passive under the sky. Asphalt, concrete, and dark rooftops absorb heat strongly, and that can warm the air above the urban core. Warmer air rises more readily, which can enhance lift when humid monsoon air is present. In some situations, this can help clouds grow taller and can increase rainfall rates over or downwind of a metropolitan area. Tall buildings also roughen the airflow, creating turbulence that can nudge storm development and influence where rain bands set up. Add urban pollution particles that can alter cloud microphysics, and the atmosphere above a city can behave differently than the countryside nearby. The outcome is not guaranteed, yet the possibility is real enough that scientists study it carefully. For residents, it can feel personal. A storm seems to keep finding the same neighborhoods, and intense rain overwhelms streets that were dry minutes earlier. The monsoon meets the city, and the city answers back. South America's monsoon helps shape rainfall across the Amazon basin. Each year, a vast seasonal shift sets the stage for South America's biggest rain engine. Moist air gathers, storms become more frequent, and the Amazon basin moves from scattered showers to a more organized wet rhythm. That matters because the Amazon is not a single place. It is a huge quilt of forests, rivers, floodplains, and cities, and each piece responds differently when the season ramps up. In some areas, the first sustained rains arrive as relief after smoky, dry months. In others, they arrive as a warning that river levels will soon climb. This seasonal pattern also influences where thunderstorms prefer to form, which changes the daily soundtrack of the region. You can think of it as a continental scale switch that decides when the forest will drink freely, when rivers will spread into floodplains, and when travel routes will change from roads to waterways. The Amazon recycles moisture and can feed storms far downwind. A rainforest does not just receive rain. It helps create the conditions for more rain. Trees pull water from the soil and release it into the air through their leaves, which adds moisture to the atmosphere above the forest. As that moist air is carried along by winds, it can help build clouds and storms beyond the Amazon itself. This is one reason weather in distant regions can be connected to what happens over the forest canopy. The process is not loud, yet it is enormous in scale. Millions of leaves act like a distributed water pump, turning groundwater into airborne humidity. On hot days, rising air can lift that moisture into cloud layers, and later it can return as rainfall. It is a looping pathway that links forest health to regional rain patterns. When you picture the Amazon, it helps to imagine not only rivers on the ground, but also a moving river in the sky. Monsoon seasons can influence river levels thousands of kilometers away. Rain that falls in one part of a continent does not stay local. Over weeks, it collects into streams, then into major rivers that carry the signal of the wet season far from where the storms first formed. In South America, that means a rise in river levels can be felt far downstream, long after a given storm has ended. Communities may watch the waterline climb day by day, even under clear skies, because the incoming flow is still traveling through the basin. This delayed surge influences fishing, boat travel, and the timing of floodplain farming. It also affects infrastructure, since higher water can stress banks, ports, and bridges. What makes it so captivating is the time lag. The monsoon can feel like it has moved on, yet its signature continues to arrive as a slow, persistent delivery of water. A season in the sky becomes a schedule in the rivers. Forest loss can reduce local moisture recycling during monsoon months. When forests are thinned or removed, The land surface changes in ways that can matter for rainfall. Fewer trees can mean less water released through leaves, which reduces the amount of moisture added to the air near the ground. The surface can also heat differently, since open areas often warm faster than shaded forest, and that can alter how air rises and where clouds prefer to form. Over time, these changes can shift how efficiently the landscape supports repeated storm development. The effect is not like turning a faucet off. It is more like changing the texture of the whole system, which can influence humidity, cloudiness, and the timing of showers in some regions. This is one reason scientists watch land use closely when studying monsoon behavior. It is not only oceans and winds that matter. The living surface below can shape how water moves from soil to air, and then back again as rain. The South American monsoon helps drive wet summers in central Brazil. In central Brazil, summer is often the season when the atmosphere finally commits to deep, frequent rainfall. Storms build in the heat of the day, and rain can arrive in dramatic bursts that cool the ground and refill local water supplies. This seasonal pattern supports agriculture across vast areas, including crops that depend on steady soil moisture through their growing stages. It also influences the cerrado, a biologically rich savanna where plants and animals are tuned to a strong contrast between wet and dry parts of the year. When the wet season is healthy, grasses grow tall and waterways persist longer into the dry months. When it is weak or erratic, stress builds quickly. City life is shaped by it too. Reservoirs, hydroelectric planning, and flood control all depend on the summer rains arriving with enough consistency. This is a monsoon story that plays out far from the Amazon's deepest forests, yet it is part of the same seasonal heartbeat. Seasonal winds can move smoke and aerosols into storm-forming regions. During parts of the dry season, smoke from fires can fill the air over large areas, and tiny particles can travel with regional winds into places where the wet season is beginning to build. When that happens, the atmosphere becomes a mix of moisture and aerosols, and clouds form inside that mixture. These particles can influence how droplets begin, how quickly they grow, and how sunlight warms different layers of air. The result can be subtle shifts in when storms ignite, or how rainfall is distributed during the transition into wetter months. It is also a human story, since smoke affects breathing and visibility long before it affects clouds. Then, when the rains arrive, they can scrub the air and bring relief, even as they create their own hazards. This movement of particles is a reminder that the monsoon is not an isolated chapter. It interacts with what came before it, including fire, land management, and the air that carries the evidence. Monsoon rains can trigger landslides where soils sit on steep slopes. On steep terrain, the wet season can turn gravity into a threat. When soils absorb water, they become heavier, and the friction that holds them in place can weaken. Add days of repeated rain, and slopes that seemed stable can begin to creep, then suddenly give way. Landslides can start as small slips that grow into fast-moving flows of mud, rocks, and uprooted trees. Roads cut into hillsides can increase risk, since they change drainage and expose loose material. The danger is often greatest where water concentrates, such as gullies, scarps, and places where vegetation has been disturbed. What makes this so unsettling is the timing. A hillside can endure hours of rain, then fail after the storm has eased, once water has had time to seep deeper. In monsoon regions, safety is not only about floods in rivers. It is also about slopes that can move when the ground becomes saturated. Wet season timing affects fish breeding in floodplain rivers. For many floodplain fish, the wet season is a doorway into new habitat. Rising water spills over riverbanks and connects channels to forests, wetlands, and shallow lakes that were unreachable during low water. Those newly flooded areas provide food and shelter for eggs and young fish, and they offer warm, productive nursery grounds. Timing matters because breeding queues are tied to water level changes and the first sustained floods. If flooding arrives late or in short pulses, fish may miss the best window for spawning and survival. If floods arrive steadily, young fish can grow in relative safety before waters retreat. This cycle ripples outward. More young fish can mean more food for birds, river dolphins, and people who fish for daily protein. It is a beautiful example of how a seasonal weather pattern shapes life histories. The monsoon does not only water plants. It opened corridors for aquatic life and sets the schedule for reproduction. The monsoon can decide whether savannas burn or stay green. Savannas live on a knife edge between growth and fire. In the dry season, grasses cure into fuel, and a spark can race across open land. When the wet season arrives with enough strength, that fuel becomes damp, new shoots replace dead stems, and fire risk drops for months. If rains are weak or delayed, the landscape can remain flammable longer, and fires can become larger and more intense. This balance affects wildlife, because many species depend on a patchwork of recently burned areas and long unburned refuge. It also affects people who rely on grazing, since green growth supports herds and reduces the need to travel farther for forage. The most fascinating part is that fire is not simply the opposite of rain. Fire is part of the savanna's ecology, and the wet season decides how often it occurs, how strongly it spreads, and what recovers afterward. A shift in monsoon timing can change the entire character of a year. Some Andean slopes receive rain mainly from monsoon-driven moisture. Along parts of the Andes, rainfall can depend on moisture that traveled a long path before it ever touched a mountain. Humid air from the lowlands is carried toward the range during the wet season, then forced upward along steep slopes. As it rises, it cools, clouds thicken, and rain falls onto valleys, farms, and cloud forests perched high above the plains. This creates striking contrasts. One side of a ridge can be lush and misty, while a nearby area sits in a rain shadow with far less precipitation. These wet slopes support unique ecosystems, including cloud forests where plants harvest moisture from fog as well as rain. They also influence water supply downstream, since mountain rainfall feeds streams that communities depend on year-round. What makes it feel almost magical is the connection across altitude. A seasonal pattern that begins with tropical humidity can end as mountain rain, shaping landscapes that seem worlds apart. Monsoons connect the ocean and land in a single breathing cycle. In one season, the ocean becomes a source and the land becomes a destination. Water evaporates from warm waves, rides inland as vapor, and returns to Earth as rain that fills soils, rivers, and reservoirs. Months later, the pattern relaxes and the flow can swing back, leaving the land to dry while the sea keeps its stored heat. That back and forth is why monsoons feel so alive. They are not random storms. They are a seasonal exchange between two surfaces that heat and cool at different speeds. You can trace the cycle in everyday places. A fishing harbor notices shifting winds. A city notices changing humidity. A mountain village notices the first reliable cloud buildups. The most awe-inspiring part is that the same basic cycle plays out across multiple continents, like the planet inhaling moisture from the sea and exhaling it over land. The monsoon circulates heat, moving energy from tropics toward poles. When monsoon clouds build, they do more than deliver rain. They help move heat through the atmosphere in a way that cools the surface and warms higher layers of air. As water vapor rises and condenses into droplets, it releases energy, and that energy powers towering storm systems that can influence weather patterns far beyond the tropics. Think of it as a seasonal conveyor belt. Warmth that began near the equator is lifted, transformed, and redistributed through winds aloft. This matters because Earth is always trying to balance an uneven heating pattern. The tropics receive more sunlight than higher latitudes, so the atmosphere and oceans constantly move energy around. Monsoon seasons are one of the most dramatic parts of that balancing act. They can even shift the positions of large-scale wind belts, which changes where clouds prefer to gather. What feels local on the ground is part of a wider process that helps regulate the planet's temperature differences. Warm oceans can load the air with moisture before monsoon onset. Before the first widespread rains, the ocean often does quiet preparation work. Warm water increases evaporation, and that steadily thickens the humidity of the air just above the sea surface. At first, the moisture is mostly invisible, and the sky can still look clear. Then, when winds begin to favor onshore flow and the land grows hot enough to lift air efficiently, that stored vapor becomes available all at once. Clouds can grow faster, and early storms can feel sudden and dramatic. This is why sailors, coastal residents, and weather forecasters pay attention to sea conditions before the season begins. A warmer surface can supply more moisture, and a cooler surface can limit it, even if the winds are ready. The ocean is like a pantry that can be stocked or sparse. When the monsoon finally arrives, the amount of moisture already waiting offshore can shape how quickly the season finds its strength. Sea surface temperatures can shift monsoon intensity from one year to another. A small change in ocean temperature can tilt the odds for an entire season. Warmer water encourages more evaporation, which can support heavier rainfall when storms develop. Cooler water can reduce that supply, and it can also change pressure patterns that steer winds. The ocean is huge, so even modest differences can influence the atmosphere across thousands of miles. This is one reason some monsoon years feel generous and others feel unsettled, even when the calendar looks familiar. It is also why forecasts often begin with maps of the sea. Those maps are not just interesting. They are clues about moisture availability, storm potential, and the strength of seasonal wind corridors. The ocean also holds memory. It changes more slowly than the atmosphere, which means its temperature patterns can persist long enough to influence weeks of weather. When people ask why the monsoon feels different this year, part of the answer may be floating right offshore. El Niño can weaken some monsoons and strengthen others. When El Niño warms parts of the central and eastern Pacific, it can rearrange tropical rainfall patterns, and that ripple can reach monsoon regions far away. In some areas, the seasonal circulation becomes less favorable for steady moisture transport, which can reduce rainfall and delay onset. In other regions, the shifted patterns can increase storminess or redirect rain belts into new places. This is one reason El Niño is watched so closely. It is not only a Pacific event. It is a global nudge that changes where rising air tends to gather and where sinking air tends to suppress clouds. The effects are not identical every time, and they can depend on the exact shape and timing of the warming. Still, the idea is powerful. A change in distant ocean temperatures can tilt the character of a season that millions of people plan around. It is a reminder that monsoons are part of a connected climate system, where faraway waters can influence local skies. La Niña often increases rainfall in several monsoon regions. La Niña is the cool phase of the same Pacific rhythm, and it can shift tropical convection and wind patterns in ways that favor stronger seasonal rains in some places. In several monsoon regions, that can mean more consistent moisture transport and a higher likelihood of widespread rainfall once the season is underway. For communities, this can be welcome, and it can also raise flood risk when rivers and soils are already primed. The seasonal story becomes one of abundance that must be managed carefully. Reservoirs may fill faster than expected. Hillsides can face longer periods of saturation. Low-lying areas can see water linger. La Niña does not guarantee any one outcome, and local weather still matters. Yet it can tilt the background conditions in a direction that makes a wet season more confident. It is like adjusting the stage lighting before the actors arrive. Storms still have to form, but the environment they form within becomes more supportive of rain. The Madden-Giuliano Oscillation can pace monsoon surges week by week. Some monsoon seasons feel like they breathe in shorter cycles inside the larger one, and the Madden-Giuliano Oscillation is one reason. It is a traveling pulse of tropical storminess that moves eastward around the globe over weeks. When that pulse arrives near a monsoon region, it can enhance cloud building and rainfall for a stretch of time. When it moves on, the same region can slip into a quieter phase with fewer storms. This helps explain why the wet season can come in bursts, with active spells followed by pauses that feel puzzling if you only think in terms of months. Forecasters watch this oscillation because it offers a way to anticipate shifts on the scale of 1 to several weeks. For people on the ground, it can shape everything from flood risk to planting confidence. The fascinating part is the sense of rhythm within rhythm. A seasonal monsoon sets the overall stage, and this traveling pulse can decide which weeks become dramatic. Monsoon rainfall is often organized into long, looping storm bands. Instead of isolated storms popping up randomly, monsoon rains can arrange themselves into sweeping bands that curve and coil across a region. These bands can persist for hours or days, feeding on a steady stream of humid air and rising motion along boundaries in the atmosphere. From the ground, it can feel like rain is arriving in organized waves, with one band passing and another forming behind it. On satellite images, the structure can look almost like braided ribbons of cloud, with bright towers embedded inside broader sheets of rain. This organization matters because it can concentrate impacts. A band that stalls over one river basin can produce prolonged rainfall, while areas just outside the band may stay comparatively dry. The looping shape can also make the season feel unpredictable to anyone watching the horizon, because the rain may appear to be moving away, then curve back again. Monsoons can be chaotic, yet they often reveal hidden geometry in how storms arrange themselves across the sky. Monsoon lows can spin into rain machines without becoming cyclones. Not every powerful rain system becomes a named tropical cyclone. Monsoon lows are lower pressure areas that can form within the broader seasonal circulation, and they can deliver enormous rainfall without developing the tight, intense core that defines a cyclone. These systems often move more slowly, which can make them especially effective at soaking one region for days. The winds may be strong enough to drive waves and bring down branches, yet the headline risk is usually water. Rivers rise steadily. Fields become saturated. Roads soften. In some cases, the cloud shield is vast, spreading rain across multiple states or provinces at once. Because these lows are part of the monsoon environment, they can form repeatedly within a season, each one arriving like another chapter of the same story. They remind us that wind speed is not the only measure of danger. A slower, broader system can be more disruptive simply because it keeps delivering rain long after the first downpour. A stronger low-level jet can accelerate moisture transport inland. Near the surface, winds can organize into fast-moving corridors that act like invisible highways for water vapor. When a low-level jet strengthens, it can move humid air inland more efficiently, supplying storm systems with fresh moisture even after earlier rain has cooled the ground. This can turn a normal rainy period into a more sustained one, because storms do not have to rely only on local evaporation. They are being fed from afar. A strong jet can also shape where rainfall focuses, since the moisture stream tends to aim towards certain regions and terrain features. In some monsoon areas, this is the difference between scattered showers and widespread organized rain. It can also raise the stakes for forecasting, because small changes in jet position can shift heavy rainfall corridors from one river basin to another. The idea is mesmerizing. You cannot see this moisture highway directly, yet it can decide where clouds build, where rivers swell, and where the season feels most intense. The Indian Ocean dipole can alter monsoon rainfall patterns. Some years, the Indian Ocean is not evenly warm. One side runs warmer than the other, and that imbalance changes where air rises most strongly above the sea. Rising air encourages clouds and rain, while sinking air tends to discourage them. When this ocean pattern sets up, it can shift the preferred pathways that carry moisture toward nearby lands. In parts of East Africa, it can tilt the odds toward heavier seasonal rains and flooding. In other areas, it can pull moisture away at the wrong time, which increases the risk of a disappointing season. What makes it so fascinating is the distance between cause and effect. A temperature difference across open water can shape river levels, crop yields, and city flood risk on land. Scientists track these changes carefully because they offer clues weeks to months ahead. The ocean is not only a source of moisture, it is also a steering wheel. Snow cover in spring can influence how quickly land heats in summer. Snow is bright, and bright surfaces reflect sunlight. When spring snow lingers across large areas, it can keep the ground cooler than usual, because less solar energy is absorbed. Cooler ground warms the air above it more slowly, and that can delay the buildup of the land-based heat patterns that help seasonal rains organize. When snow melts earlier, darker soil and rock are exposed sooner, and the land can heat faster, which can strengthen the contrast between land and sea. That contrast matters for the timing and vigor of monsoon circulation in some regions. It is a beautifully indirect connection. A late spring snowpack in distant mountains or high plains can influence summer humidity and storm development far away. This is one reason climate scientists care about snow maps, not just rain maps. The spring landscape can help set the stage for what summer becomes. Aerosols can brighten clouds and sometimes suppress rainfall locally. Tiny particles in the air can change how clouds behave. When there are more particles available, clouds can form with many smaller droplets rather than fewer larger ones. Smaller droplets tend to stay suspended longer, which can make clouds look brighter and whiter because they reflect more sunlight. In some conditions, that same shift can make it harder for droplets to grow large enough to fall as rain right away. The cloud may persist, drift, and release precipitation elsewhere, or it may evaporate before producing much rain at all. The effect is not simple and it varies by cloud type and environment, yet it matters enough to influence local rainfall patterns near polluted regions. It is also a striking example of scale. A droplet is microscopic. A cloud is city-sized. A monsoon system can span a continent. Small particles can still nudge the outcome by changing the cloud's internal machinery. Black carbon on snow can speed melting and change regional heating. Black carbon is a dark soot-like particle produced by incomplete burning, and it can travel through the atmosphere and settle onto snow. When that happens, snow becomes less reflective and absorbs more sunlight. That extra absorption can speed melting, which changes how long bright snow cover remains on the land. Earlier melt can expose darker ground sooner, which can warm rapidly and alter temperature contrasts that influence seasonal wind patterns. It is a chain reaction. A thin layer of dark particles can change melt timing. Melt timing can change land heating. Land heating can change how air rises, and how moisture is drawn in during warm months. This connection is one reason scientists study not only greenhouse gases, but also short-lived pollutants that affect sunlight and surfaces. It is also a reminder that the monsoon is sensitive to the boundary between land and air. Change the surface, and the season can respond. Monsoon prediction improved when satellites began tracking ocean winds. Before satellites, vast parts of the ocean were poorly observed. Ships provided valuable reports, yet the coverage was sparse and uneven. Satellites changed that by watching clouds, sea surface patterns, and winds over wide areas day after day. With better knowledge of wind fields over the ocean, forecasters gained a clearer view of how moisture transport was setting up before it reached land. That matters because monsoons often depend on persistent wind corridors that feed storms inland. Satellites also help identify developing low-pressure areas and organized cloud bands that can bring multi-day rainfall. Over time, this steady stream of observation improved models, because models can be corrected and tested against what the atmosphere actually did. The result is not perfect prediction, yet it is a major leap from guesswork to guided expectation. People who manage water, crops, and flood response now have better lead time, thanks to eyes in orbit. Weather radars reveal how monsoon storms grow, merge, and collapse. A radar does something almost magical. It lets you see rain inside clouds, even at night, and it shows the structure of a storm as it evolves minute by minute. In monsoon season, this matters because storms often build in clusters, then interact. One cell can weaken while another strengthens nearby, and outflow wind can trigger new development along their boundaries. Radar can reveal those boundaries as arcs of rain and wind-driven spray, which helps forecasters anticipate where the next burst may form. It also helps identify dangerous intensification, when a storm suddenly begins dumping heavier rain over the same area. For flood warning, those minutes matter. For aviation and outdoor safety, they matter too. Radar is also a teaching tool. It turns the sky into a readable story, showing how storms are not isolated objects. They are living systems that collide, share energy, and sometimes collapse into calm. Seasonal forecasts blend ocean data with atmosphere models to estimate monsoons. A seasonal forecast is not a promise about next Tuesday. It is an informed estimate of how the coming months may tilt toward wetter or drier conditions. To build that estimate, scientists combine observations of the ocean, the land surface, and the current state of the atmosphere, then use computer models to simulate many possible futures. The ocean is especially important because it changes slowly and can carry signals that last for months, such as warm patches that influence evaporation and winds. The models also track how heat and moisture may move through large-scale circulation patterns. Forecasters often run ensembles, which are many versions of the forecast with small differences in starting conditions. If many versions point in the same direction, confidence rises. These forecasts help governments plan water releases, farmers choose crops, and disaster agencies prepare. They also highlight uncertainty honestly, which is part of what makes them trustworthy. The monsoon is complex, yet it leaves clues that models can learn to read. Monsoon onset is easier to feel than to define mathematically. People often know it in their bodies before it shows up neatly in a statistic. The air turns heavier. Nighttime breezes change direction. Clouds begin to build earlier in the day, and the first steady rains shift the soundscape of a place. Scientists still need definitions, so they use thresholds like sustained wind changes, humidity increases, and patterns of rainfall over a period of days. Yet the atmosphere does not always cooperate with clean lines. A region can get early storms that feel like the start, then slip back into dryness. Another year, the change is gradual, with no single dramatic day. That is why onset dates can differ depending on the method used and why local experience remains valuable. Farmers and sailors have long tracked signs that are practical rather than mathematical, because decisions cannot wait for perfect definitions. The fascinating truth is that a monsoon is a transition, not a switch. It has a leading edge, full starts, and a settling in that varies by region. Some monsoon changes are linked to shifts in the jet stream. High above the ground, fast winds in the upper atmosphere act like traffic lanes for weather systems. When the jet stream shifts position or strength, it can change where rising and sinking air prefer to set up, which influences storm formation and rainfall corridors. In some monsoon regions, an upper-level pattern can either support widespread thunderstorm development or suppress it by promoting dry, stable air aloft. The jet stream can also help steer the tracks of disturbances that trigger multi-day rain events. This is one reason monsoon seasons can be sensitive to patterns far beyond the tropics. A change in the upper atmosphere can influence how easily humid air can rise and condense. For people on the ground, the jet stream is invisible, yet its effects can be felt in the pacing of rainy spells and breaks. It is like a high-altitude conductor shaping the tempo of the season's storms. Climate warming can intensify extreme rain even if totals change little. Warmer air can hold more water vapor, which means that when conditions are right for rain, the atmosphere may have more moisture available to release in a short time. That can increase the risk of very heavy downpours, even in places where the overall seasonal rainfall does not change dramatically. For monsoon regions, this matters because the biggest harms often come from intensity, not just totals. A season with the same total rain can be far more dangerous if more of that water falls in fewer, stronger events. Faster runoff can overwhelm drains and rivers, and saturated slopes can fail more easily. It can also challenge farming, because intense rain can erode soil and damage seedlings, while still leaving long dry breaks between storms. Scientists study these changes carefully because they affect infrastructure design and disaster planning. The monsoon may keep its familiar season, yet the character of its heaviest moments can shift. Monsoons have guided trade routes across the Indian Ocean for centuries. Long before engines and modern forecasts, merchants learned that the sky had a schedule. Seasonal winds could carry ships from East Africa and Arabia toward India and onward to Southeast Asia. Months later, the direction would change, opening a route home. That predictability turned the ocean into a stitched network of ports, markets, and languages that met on the tide of air. Spices, textiles, ceramics, and ideas moved with the same winds. Coastal towns grew into trading hubs because they sat at the right crossroads of sea lanes and seasonal timing. Sailors did not need to conquer the ocean's randomness. They needed to understand its rhythm. In that way, monsoons acted like a maritime road system, drawn not on land, but in the atmosphere. When the winds arrived, commerce moved. When they shifted, the ocean waited. Sailors once relied on monsoon timing to travel east, then return west. A wooden ship could not argue with the wind. If you left at the wrong time, you might stall, drift, or be forced into dangerous improvisation. So captains planned departures around seasonal changes that could be counted on more reliably than day-to-day weather. The journey was not only about distance. It was about patience and timing, because the return trip could be impossible until the winds reversed. That meant crews often stayed in foreign ports for weeks or months, which shaped local economies and cultural exchange. Markets adjusted to the arrival of fleets. Shipyards repaired hulls during the waiting season. Communities grew used to the presence of outsiders who were not passing through quickly, but living within the monsoon calendar. This dependence on timing also created a kind of shared knowledge across the ocean. People who had never met still relied on the same invisible change in wind direction to get home. Ancient farmers built tanks and canals to store monsoon water. In regions where most rain arrives in a concentrated season, storing water can be the difference between stability and hardship. Long ago, communities engineered solutions that matched their landscapes. They carved channels that guided runoff into fields, and they built earthen embankments that held water in man-made lakes and ponds. These systems captured the season's surplus and stretched it into the dry months, supporting crops, livestock, and daily life. What makes this so impressive is the planning. Builders had to understand slopes, soils, and the way floods move across land. Maintenance became a social practice, not a one-time project, because silt and storms constantly tested the infrastructure. In many places, these structures also shaped settlement patterns. Villages grew around reliable storage, and farming expanded where water could be managed. The monsoon did not only bring rain. It inspired civil engineering that turned timing into security. Monsoon calendars shaped festivals, taxes, and planting traditions. When a season determines food and water, it naturally becomes a marker of time. In many monsoon regions, communities built calendars around the expected arrival of rain and the phases of planting that follow. Celebrations often clustered around the first dependable storms, because that moment signaled hope and a new agricultural cycle. Governments and rulers also paid attention, since harvest outcomes influenced revenue and stability. Taxes might be assessed with an eye to seasonal success, and obligations could be timed to when travel was possible between wet periods. Even social routines adapted. Weddings, long journeys, and major construction were often planned for drier windows when roads held and rivers were lower. This is not superstition. It is practical adaptation to a predictable pattern that still has uncertainty year to year. The monsoon became more than weather. It became a shared clock that organized labor, celebration, and planning across generations. City drainage systems often fail when monsoon rain falls too fast. A city can handle a lot of water if it arrives slowly. The trouble begins when intense rainfall overwhelms the speed at which streets and pipes can move it away. Water rushes toward low points, carrying litter and sediment that can block grates and narrow channels. Underpasses fill quickly. Small streams in urban corridors can jump their banks. Even well-designed systems can struggle if land surfaces have been covered with concrete, because water has fewer places to soak in. The most stressful moments are often brief. A violent downpour lasting half an hour can cause more disruption than a full day of light rain. People experience it as sudden chaos. Traffic stalls, basements flood, and emergency crews race to clear blockages. Afterward, the city dries, but the cost remains in damaged goods and strained services. Monsoon rainfall exposes the difference between average conditions and peak intensity, and cities are built for averages unless they plan otherwise. Floodplains can be fertile because monsoons deliver fresh silt each year. When rivers overflow during the wet season, they do not only spread water, they also carry fine sediments eroded upstream, then deposit those particles across floodplains as the water slows. That thin layer can replenish soils with minerals and organic material, which supports productive farming in many river valleys. This is one reason floodplains have attracted people for thousands of years, despite the obvious risk. The same process that can damage homes can also renew the ground for crops. Over long periods, repeated deposition can even build the land itself, shaping deltas and broad flat valleys that are easy to cultivate. The timing matters too. After waters retreat, farmers may plant into moist, enriched soils that hold water better than surrounding uplands. The monsoon becomes a kind of natural soil delivery service, moving nutrients from mountains to plains. It is a reminder that floods are not only destruction. They are also one of the ways landscapes stay alive and productive. Monsoon floods can recharge groundwater better than brief winter rains. Groundwater is slow water. It refills best when moisture has time to soak deep rather than run off the surface. During monsoon season, repeated rainfall and widespread flooding can keep the ground wet for long enough that infiltration continues day after day. Floodplains, wetlands, and even irrigated fields can act as recharge zones, allowing water to seep downward into aquifers that store it for months or years. In contrast, short winter rains in many regions arrive in cooler, drier air, and they may fall in scattered events that do not saturate soils for long. Recharge also depends on geology. Sandy soils can absorb quickly, while clay-rich layers slow the process. Human infrastructure can help or hinder. Paved surfaces reduce infiltration, while managed recharge basins can increase it. The important point is that the monsoon does not only fill rivers you can see, it can also refill hidden reserves that keep wells flowing long after the last storm cloud has passed. Hydropower output in many countries rises and falls with the monsoon. A hydropower plant is ultimately a machine that converts moving water into electricity. During monsoon months, inflows can surge, reservoirs rise, and turbines may run at higher capacity. That can lower the cost of power and reduce reliance on fossil fuels during the wet season. The flip side is vulnerability. If rains are weak, reservoirs may not refill, and power generation can drop at the same time that heat increases electricity demand. Operators also face trade-offs during strong seasons. They must balance flood control with storing water for later, and they must coordinate releases so downstream communities stay safe. This makes the monsoon a major factor in national energy planning. It shapes when power is plentiful, when it is tight, and how grids manage risk. For many people, the link is invisible. Lights turn on or do not. Yet behind that simple experience, seasonal rainfall is influencing megawatts, prices, and long-term infrastructure decisions. Monsoon failures can increase heat stress by removing cloud cover. Clouds act like shade over a whole region. When the wet season is weak, skies can stay clearer, and sunlight hits the ground more directly for longer stretches. Daytime temperatures can climb higher, and the relief that usually comes from frequent storms may not arrive. Heat stress is not only about temperature. It is also about how long the heat lasts and how little recovery happens at night. In some places, a failed season can mean hot spells that stretch across weeks, which strains bodies and increases risk for older adults, outdoor workers, and anyone without reliable cooling. Agriculture feels it too, because plants lose more water through their leaves in hotter conditions, and irrigation demand rises. Cities can become especially dangerous, since paved surfaces store heat and radiate it after sunset. When people talk about a bad monsoon, they often mean missing rain. They may also mean missing the protective cover that usually tempers the harshest heat. Successful monsoon years can reduce dust by locking soil to plants. Dust is easiest to lift when soil is dry, loose, and bare. A strong wet season changes that in several ways. Moisture helps bind soil particles together. A new plant growth covers ground that would otherwise be exposed to wind. Roots also hold soil in place, especially in grasslands and croplands that green up after reliable rains. The result can be fewer dust storms and clearer air over wide areas, which has real benefits for health and visibility. It can also affect transportation and even solar energy performance, since airborne dust can reduce sunlight reaching panels. There is a feedback here too. Less dust in the air can change how sunlight warms the surface, which can subtly influence local temperature patterns. The key idea is simple and satisfying. When water arrives on time and in enough quantity, the landscape becomes more anchored. The monsoon does not just add water. It can quiet the atmosphere by giving the ground a living grip. Monsoon seasons can influence malaria risk by changing mosquito habitat. As rains return, shallow pools appear in footprints, ditches, paddies, and roadside ruts. Many mosquito species thrive in these temporary waters because they warm quickly and can be free of fish that would eat larvae. When the wet season arrives in pulses, new pools keep forming, which can extend breeding opportunities across weeks. Human behavior shifts too. People may sleep with windows open for relief from humidity, or spend evenings outdoors after cooler rain. Both changes can increase exposure if protection is not used. Health teams often watch rainfall patterns because they can hint at when risk may rise, even before clinics see a surge. The story is not simple, since heavy floods can wash breeding sites away while steady standing water can expand them. Still, the link is powerful. A seasonal wind system can quietly shape a disease landscape by deciding where water collects and how long it lingers. Cholera outbreaks can follow floods when clean water systems are disrupted. Floodwater moves fast, and it does not respect boundaries between sewage, surface runoff, and drinking water sources. During major monsoon floods, pipes can break, wells can be contaminated, and treatment plants can be overwhelmed or lose power. When people are forced to use unsafe water, a single contaminated source can spread illness through whole neighborhoods. The risk can be highest after the dramatic flood peak, when standing water remains and sanitation is strained, yet attention begins to drift. Rapid response matters. Safe water distribution, chlorination, and clear public guidance can prevent a surge from becoming an outbreak. The tragedy is that the trigger is often not the rain itself. It is the way flooding disrupts the systems that normally keep water separate and clean. In that sense, the monsoon reveals the hidden plumbing of society. A storm can turn health into an infrastructure story overnight, and recovery depends on rebuilding trust in the water people drink. Wet season humidity can increase mold and indoor air problems. When humidity stays high for long stretches, homes can struggle to dry. Damp walls, wet furniture, and trapped moisture in carpets or bedding can become a perfect setting for mold to grow, especially in rooms with poor ventilation. The effects can be subtle at first. A musty smell appears, then irritation, coughing, or worsened asthma in sensitive people. In crowded housing, the problem can spread quickly because many households cannot run dehumidifiers or keep spaces airy during frequent rain. Building materials matter too. Untreated wood and porous plaster can hold moisture, while well-sealed surfaces shed it. Prevention often comes down to small habits that become crucial in monsoon months. Drying clothes outdoors may be impossible, so indoor drying needs airflow. Fixing leaks becomes urgent, not optional. The wet season changes health risks in ways that are easy to overlook because the hazard is inside the home rather than in the sky. Landslide risk rises when soils stay saturated for many days. A hillside can absorb rain for a while, then reach a tipping point where the ground loses strength. Water fills poor spaces between grains, which reduces friction and increases weight at the same time. On steep slopes, that combination can turn slow creep into sudden motion. The most dangerous slides often happen after repeated rainfall, not during the first storm, because infiltration needs time to reach deeper, weak layers. Warning signs can be small. New cracks appear, doors jam, trees lean, and muddy water seeps from the ground where it never did before. Roads cut into hillsides can make things worse by concentrating drainage and undercutting support. The sound can be startling, like thunder that comes from the earth. In monsoon regions, landslides are a companion hazard to floods, and they can strike at night when storms are loud and visibility is low. Understanding saturation, not just rainfall totals, is key to staying safe. Early warning systems now use rainfall thresholds to trigger evacuations. In many places, disaster response has shifted from reacting to flooding toward anticipating it. One approach is the rainfall threshold. If rain intensity or accumulated rainfall passes a set level over a watershed, alerts escalate because the odds of dangerous runoff rise sharply. These thresholds are built from past events, local terrain, soil type, and drainage behavior, and they are refined as more data arrives. Radar and satellite estimates can fill gaps where rain gauges are sparse, and river sensors can confirm when water is rising faster than normal. When the system works, it buys time. Families move to higher ground before roads cut off. Emergency services stage resources before the first calls. The fascinating part is that the trigger can be invisible to the public. A number on a dashboard can set a whole evacuation in motion because it represents hard-earned knowledge about how that landscape responds. A monsoon storm becomes actionable information, not just a dramatic sky. Some monsoon regions face both sea flooding and river flooding together. In coastal deltas and low-lying cities, water can attack from two directions at once. A storm pushes heavy rain into rivers upstream, while the sea level at the mouth can be high from tides or storm surge. When outflow is blocked, rivers rise higher than they would inland, and drainage canals back up into streets. Even without a major cyclone, persistent onshore winds can pile water along a coast and slow river discharge. The result is compound flooding. It is not simply more water. It is water with nowhere to go. This is why the same rainfall amount can cause mild ponding one week and severe flooding another, depending on the ocean's timing. Managing it requires coordination across agencies that do not always work together, including flood managers, port authorities, and meteorological services. It also changes how communities prepare. Sandbags are useful, yet tide charts can be just as important as rainfall forecasts. The monsoon becomes a meeting point for land hydrology and coastal physics. Reservoir managers must balance flood control with saving water for dry months. A reservoir is a promise for the future, yet it can also become a threat during extreme rain. If the lake is kept too full, incoming monsoon flows may force sudden releases that flood downstream communities. If it is kept too empty, there may not be enough stored water for the dry season, when cities and farms depend on reliable supply. Managers make decisions under uncertainty, using forecasts, inflow measurements, and rules that may have been designed for a different climate. The choices are stressful because both outcomes carry real costs. Releasing water early can look wrong if rains fade. Holding water can look wrong if a deluge arrives. Communication becomes part of the job. Downstream residents need notice, and upstream communities need clarity about why levels are changing. The reservoir becomes a living negotiation between safety now and security later. In monsoon countries, dam operators do not just manage water. They manage risk, trust, and timing. Monsoon clouds can reduce solar power output, even as hydropower rises. Energy systems feel the monsoon in a surprisingly direct way. Thick cloud cover lowers sunlight, which can cut solar generation during the very months when rain is most persistent. At the same time, rivers and reservoirs may be gaining inflow, which can increase hydropower potential. That creates a seasonal swap. One renewable source dips while another rises. Grid operators can take advantage of this complementarity. but only if transmission and planning are strong. The challenge is timing. A stormy week can reduce solar sharply, while hydropower may respond with a lag as water travels through a basin. Storage, forecasting, and flexible demand become valuable tools. Even maintenance schedules may shift, since working on solar fields or transmission lines can be harder during frequent storms. The monsoon reminds us that electricity is not abstract. It is tied to clouds, rivers, and the daily weather that people can feel. A season of rain becomes a season of energy choreography. A delayed monsoon can shift migration patterns for birds and insects. Many species time movement to food and water that appear with seasonal rains. When rains arrive late, flowering, insect hatches, and fresh plant growth can also be delayed. Birds that depend on insects may linger longer in one region or arrive to breeding grounds when food is not yet abundant. Insects that follow wet soil, like some butterflies and dragonflies, may shift their routes toward areas that received earlier storms. These changes can ripple outward. Predators miss prey peaks. Pollination timing drifts. Wetland birds arrive to shallows that are still dry. People notice too, especially in places where seasonal migrations are culturally familiar. A delayed arrival of a well-known bird can feel like a calendar slip in nature. The science is a reminder that migration is not only about temperature. It is also about rainfall timing, and the monsoon can act like a signal flare that tells living things when the landscape will open its next buffet. Monsoons remind us that weather is not random, it has seasons. Day-to-day weather can feel chaotic, yet monsoons reveal a deeper order. They show that the atmosphere can organize itself into repeating patterns that return each year with recognizable timing and structure. Winds shift direction, humidity rises, cloud belts form, and the whole system behaves like a seasonal machine that can be studied, anticipated, and lived with. That does not mean it is perfectly reliable. It still varies, and that variation matters. Yet the existence of the pattern is itself awe-inspiring. It is proof that Earth's climate has rhythms that connect heat, water, and motion across huge distances. People have built calendars, crops, shipping routes, and cities around this repeating pulse because it is dependable enough to plan for. Listening to a monsoon season is like hearing the planet's logic made audible in wind and rain and changing light. It reminds us that the sky follows rules, even when it surprises us. As we come to the end of our journey through monsoons, you can let the idea of them settle into something simple and steady. A seasonal turning of winds. Ocean water lifted into air. Heat rising from land. Then clouds gathering and rain returning, right on the edge between promise and power. We wandered across continents where whole harvests depend on timing, and where rivers swell and spread into floodplains that feed the soil. We followed moisture inland over mountains that squeeze it into downpours, and across deserts where a single storm can wake a dry riverbed in the dark. We listened for the bigger patterns too, the ones that link distant oceans to local skies, and tie human history to weather that repeats with the year. If you are still awake, and you would like another peaceful thread of science to follow, there is a next video waiting for you on the screen. You can let it play, or save it for another night. And if this episode helped you unwind, you might like to support the channel in a small way. You could leave a kind comment, share it with someone who loves learning at bedtime, or subscribe so these stories find you again. But for now, you do not need to hold on to any details. Let them drift like clouds thinning after rain. Allow your jaw to unclench. Let your shoulders drop. Feel the weight of your body supported beneath you, and let your breathing return to its own calm pace. The winds can turn without you watching. The season can arrive without you counting the days. You have done enough for today. Sleep well and good night.